Good morning all. Can you hear me?
Yes, madam.
Okay. So sorry for the inconvenience due to the power failure. I couldn't start at time. So let's start the lecture without wasting time, right? So last day we discussed two continuous distributions, namely continuous uniformly distribution and exponential distribution. So in the uniform distribution, so within the given interval, the distribution is a constant, right? So we can write the distribution as 1 over b minus a when b is the upper limit and a is the lower limit. And the exponential distribution gives us the waiting time until the first success, right? Waiting time until the first success. So it's discussing about a rate, right? So there we found the probability of random variable waiting time until the first success in a Poisson process, right? The rate or the mean we denoted using the lambda. And today we are going to discuss the next distribution, gamma distribution, right? Gamma distribution is also an extension of the exponential distribution. So in a Poisson process with mean lambda, the waiting time until the first success or the first change has an exponential distribution, right? We know that, we discussed it earlier. So let x be the waiting time until the alpha success. Now the random variable changes into waiting time until the alpha success. In exponential distribution, it's first success. And until the alpha success, if the random variable x in a Poisson process with mean lambda, it follows a gamma distribution, right? You can remember that in a geometric distribution, there we are taking the random variable x as number of trials until the first success. And extension of that, the binomial distribution, number of trials until the nth success, right? Likewise, here also in exponential distribution, it's the random variable is the waiting time. Now it's a continuous one now. So waiting time until the first success in a Poisson process with mean lambda, it follows an exponential distribution. And waiting time until the alpha success in a Poisson process with mean lambda, it follows the gamma distribution. So using a mathematical process, we can show that fx takes the form in the following definition. So we directly go into the definition without talking the background. So it's somewhat difficult to understand. So straightforward, I'm giving you the definition, right? So a random variable x has a gamma distribution and it is referred to as a gamma random variable if and only if its probability density is given by this function. So it is fx equals to 1 upon, so this is the gamma of alpha. Gamma of alpha, it's read as a function. So it's a function actually. So this is a function, gamma of alpha into theta to the power alpha multiplied by x alpha minus 1 e to the power minus x over theta, right? So here it is for x greater than 0 and elsewhere it is the function is 0. So here alpha is also greater than 0 and theta is 1 upon lambda. Lambda is the mean number of successes in the unit interval in a Poisson process, you know that. And theta is the mean waiting time, that is equals to 1 over lambda. So hence the waiting time x until the alpha success or the alpha change in a Poisson process has a gamma distribution with parameters. Now we have two parameters, alpha and theta. Alpha is the alpha success, right? Waiting time until the alpha success. How many successes have been occurred? It's the alpha, and theta is the mean waiting time, right? Mean waiting time for the first success that is obtained using 1 upon 1 over lambda, right? So here the gamma function, gamma of alpha is denoted like this. The gamma function denoted by gamma of t for all t greater than 0, that is given by this function. So this is the gamma function, right? So the gamma function has these properties. Since the integrand is positive, so what is the integrand? The thing inside the integration sign, this one, the integrand. Since the integrand is positive, gamma of t greater than 0 and greater than 0 for t greater than 0. That is the first one. And then values of gamma of t are often given in tables of integrals, right? In tables of integrals, we can find this gamma function, gamma of t, right? So if t is greater than 0, when t is greater than 0, let's see what happens. We can integrate it by parts like this. So it is y to the power t minus 1 into e to the power minus y. Limit goes from 0 to infinity plus 0 to infinity t minus 1 y to the power t minus 2 e to the power y minus y dy. So it is by integration by parts, right? So we can, after solving this, we can take t minus 1 out, and it is 0 to infinity y to the power t minus 2 into e to the power minus y dy. Right. So the gamma of t is this. This is gamma of t minus 1. So if gamma of t is integration from 0 to infinity y to the power t minus 1 e to the power y. So if it is integration y to the power t minus 2 into e to the power minus y, it should be the gamma of t minus 1. Okay, so now gamma of t can be written as t minus 1 into gamma of t minus 1. Okay. So according to that results, we can write when t is equals to n a positive integer, when n is a positive integer, using the above results, we can write this as n minus 1, n minus 1 into gamma of n minus 1. So gamma of n minus 1 again can be written as n minus 2 gamma of n minus 3. So likewise, we can go up to 2, 1, And finally, gamma of 1. Right? So the gamma of 1 is 0 to infinity e to the power minus y dy. So that is equals to 1 using the definition. So finally, gamma of n, for n is positive integer, we can write it as the factorial n minus 1. So this is how gamma function works. And using some calculations, we can show that gamma half is equals to square root of 5. So this is the notation of gamma function. X is a gamma distribution with parameters beta and alpha. So here theta is mean waiting time and alpha is the success, right? Yes. Mean number of theta is mean waiting time. And alpha is the number of success, alpha success, right? So this is the graphical representation of the gamma distribution. So in the gamma distribution, there are 3 basic shapes depending on the alpha, right? Depending on the value of the alpha, the gamma distribution has 3 basic shapes. So when alpha is less than 1, there is a shape, and for alpha is 1, there is another shape, and when alpha is greater than 1, the shape again different, right? So this is the gamma distribution function. So for an example, here the graph takes the following shapes for alpha 0.5, that is a value less than 1, and alpha equals 1 and 2, that is alpha greater than 1, right? So this is the curve for the gamma distribution when alpha less than 1. So note that if alpha is less than 1, y-axis is an asymptote. So what is the meaning of asymptote? So it's approaching a value. See here, it's approaching a value. So it is called asymptote. So when alpha is less than 1, the gamma distribution y-axis is an asymptote, right? So when alpha is equal 1, so this is the alpha equal 1. Right? When alpha equals 1, so when x equals 0, it has a value that is equals to 1 over theta. When alpha equals 1, when x equals 0, it has a value that is 1 over theta. And if alpha is greater than 1, so this is the curve. When alpha is greater than 1, when x is 0, right, then the gamma function is also 0. So according to the value of alpha, there are 3 basic shapes for the gamma distribution. Right? Okay, let's move on to Next section, mean, variance, and the moment generating function. So we want to find the mean, variance, and moment generating function. Okay. So expected value of x, as usual, we can write it as 0 to infinity, x into the gamma distribution function, the density function, right? The density function, x alpha minus 1 e to the power minus x upon theta divided by gamma of alpha into theta to the power alpha dx. So we can take gamma of alpha out here and then 0 to infinity. These two simplify into x alpha e to the power minus x over theta divided by theta to the power alpha dx. So we rearrange this. We are going to rearrange this like this. So here we can take theta also out. This one divided by alpha plus 1. And theta alpha plus 1. Okay. So we rearrange it into dx. So this part now, the integrand, so it is fx, the gamma x theta comma alpha plus 1. It is the gamma function of theta alpha plus 1. So if we integrate that one from 0 to infinity, it is the total probability of gamma function. So this whole part is equals to 1. Okay. Then the gamma of alpha plus 1 could be written as alpha into gamma of alpha divided by gamma of alpha into theta. So these two cancels out and the expected value is alpha theta. So in the gamma distribution, the expected value for the mean is equals to alpha theta. Right. So in the same manner, we can obtain the variance as well. And the variance of the random variable x in the gamma distribution is equals to alpha theta squared. So next, the moment generating function. So the moment generating function, again, from 0 to infinity, e to the power tx into the gamma density function dx, right? Then simplify it into simplify and take this. Okay. Then by substituting u and x, finally we obtain this expression for the moment generating function. So use the knowledge of integration. Okay. So there is a special case of the gamma distribution. So this is the gamma distribution. So when alpha is equals 1 in gamma distribution, when alpha is equals 1, so the gamma of alpha, that is gamma of 1 is equals 1. Then the function is reduced to the exponential distribution. When alpha is 1, it reduced to the exponential distribution. So it's obvious, right? So in exponential distribution, we are taking the first success. So there alpha is equals 1. So the gamma distribution reduces into the exponential distribution when alpha is equals 1. Right? So then we let nu as a positive integer. Nu is a positive integer. When alpha is equals to nu over 2, right? The function could be written like this. When nu is equals to, alpha is equals to nu over 2, where nu is a positive integer, and theta is equals to 2, right? Then this is called the chi-square distribution with new degrees of freedom. So in later, you are going to, in second semester, I guess, in second semester, you are going to learn the chi-square distribution. So gamma distribution reduces into the chi-square distribution when alpha equals nu over 2, where nu is a positive integer and theta is equals to 0. So in the chi-square distribution, mu is alpha theta. So alpha theta is now nu over 2 into 2. It's nu. And the variance sigma squared, alpha theta squared, it is 2 nu. Okay, so it's there are two special cases when alpha is equals 1, gamma distribution reduces into the exponential distribution, and when alpha is a nu over 2, where nu is a positive integer and theta equals 0, it reduces into the chi-square distribution with new degrees of freedom. Okay. So someone has asked me whether they want to name this proof. It's better to know, right? It's better to know to prove mean, variance, and moment generative function for the distributions, right? It's better to know. Right. So any problem? relate to the gamma distribution. So that is the gamma distribution, right? So waiting time until the alpha success, the random variable gives us a gamma distribution. Okay. So let's move on to some examples. Okay, try this example. So it's an example for exponential distribution. Try this example. I'll give you 5 minutes. So someone has asked me to explain the chi-square distribution again. The chi-square distribution, so in the gamma, so chi-square distribution is again another sampling distribution. Sampling distribution, you will learn it under this in this next semester, Introduction to Statistics and Computed 2. It's a sampling distribution, right? It's a sampling distribution. So they are the chi-square distribution. There are widely used techniques using the chi-square distribution. So here just you have to know that we can reduce the gamma distribution into chi-square distribution when the value of alpha in gamma distribution is equals to nu over 2, where nu is a positive integer, and theta equals 2 in the gamma distribution, right? Then it follows a chi-square distribution with mu degrees of freedom. That's the thing you want to know. Not beyond there, right? Okay, do this example. Actually, I want to give you a special announcement. So today's the last day I am doing this lecture series because I am about to take leaves from next week onwards. So your lecture will be conducted by Mr. Lakshana Ponsu, Lakshana sir. So he will take the lecture from next week onwards. So most of the things actually I have covered now. 36 hours have been covered now. The only thing left is normal distribution and some applications of normal distributions. There is another note to come. So next week onwards, please follow the LMS, right? Regularly access to the LMS and updated. He will upload all the materials and he will conduct the lectures, right? And also I'll give you a feedback form as well in near future. So please fill that one also. Okay, try this example. There are some people who couldn't attend to the quiz, right? So those who couldn't attend to that quiz, please give your names to the tutor, right? It's better if you can give your name today itself. Give your name and the index number to the tutor, so then we can arrange another quiz for them. So please message to your tutor your index number and the name. So the problem, it says, suppose the distribution of the lifetime of camera flash batteries X is exponential with mean or the average lifetime of 1/3, 1/3. The average lifetime. So it's not lambda, it's theta, right? Average or the mean lifetime. It's not about a rate. So if it's given using a rate, we can choose it as lambda, but here it's mean lifetime, average lifetime. So it's the theta, right? So theta is equals to 1/3. Find the chance batteries last at least 10 hours. Find the chance that batteries last at least 10 hours, right? That means you have to find the probability of X greater than 10. right? So it is same as writing x less than or equals to 10. Okay. So this is equals to 1 minus from 0 to 10. The form minus, right? So we know the function is fx equals 1 over theta e to the power minus x upon theta dx. Okay. So it is now 1 over 3, that is 3 into e to the power minus 3x dx. So this can be written as f10, right? Why? So if the density function is this, the cumulative probability, cumulative function or the distribution function, that is equals to from 0 to an arbitrary point 1 over theta e to the power minus x over theta dx. So by integrating this, we can directly obtain it as 1 minus x over theta. Right? So we can just substitute that value here and input the limits. Right? So it is either you can integrate this one and apply the limits, or else directly you can use this f10. So that is, if we use f10, that is 1 minus e to the power 1 upon theta is 3 minus 3 into 10. So it is e to the power minus 30. It is asking batteries last at least 10 hours. At least 10 hours. So it is here, it's greater than 0, right? Not greater than or equals to. At least 10 hours. 10ක්වත් ඉන්න ඕනේ. එතකොට ඒ කියන්නේ 10 අවම ගාන ඒ කියන්නේ 10ක් ඉන්න ඕනේ. 10ට sorry, find the chance batteries last at least 10 hours. 10ක් තියෙන්න ඕන අනිවාර්යෙන්ම. Right? එතකොට sorry, කඩෙන් බලන්න find chances batteries. Yes, 10ක් අනිවාර්යෙන්ම තියෙන්න ඕනේ. එතකොට 11 වෙනි පැයේ ඉඳලා තමයි, ඒ කියන්නේ 10ට වඩා ඉඳලා තමයි යා බැටරි එක ඩෙඩ් වෙන්න ගන්නෙ. 10ක් අනිවාර්යෙන් තියෙන්න ඕනේ. ඒ කියන්නේ ෆස්ට් සක්සස් එන්නේ 10න් පස්සේ. Right? First success එක එන්නේ 10න් පස්සේ. That's why it's mentioned here x greater than 10. So here the random variable is failure of batteries, right? Failure of batteries after 10 hours. So it lasts 10 hours. After the 10 hours, it starts today. So therefore, it should be x greater than 10. So lifetime of a battery should last 10 hours. So after that only start to failure. So failure is the first success in this exponential distribution. Right? I think now it's clear. So in exponential distribution, it gives us waiting time until the first success. Give me a second. Right? So is there any problem? So in exponential distribution, it gives the waiting time until the first success, right? So here battery is getting failure is the first success. So first success occurs after the 10 hours. So that's why we want to find here the probability where x greater than 10. Okay. So the next one, find the chance batteries last at least 15 hours, given that they have already lasted at least 5 hours. So here it's a conditional probability problem. So probability where x is greater than 15, given that x is greater than 5. So the information given is battery have already lasted at least 5 hours. So we want to find the probability or the chance batteries last at least 15 hours. Okay. So we can write it as P x greater than 15 and x greater than 5. Using the conditional probability definition, and this one is equals to 15 greater than 5, right? So this is 1 minus f15, 1 minus f5. Why? We can write E x greater than 15 as 1 minus probability x less than or equal 15. and p x greater than 5, 1 minus p x is less than or equals to 5. Okay. So this is F15 and this is F5. So F1 minus F15 is 1 minus e to the power minus 3 into 15, 1 minus e to the power minus 3 into 5. So power 10. And without using this conditional probability, we can just use the no memory property. Right? Can you remember the no memory property in where? Hypergeometric distribution, I guess, right? So as in that one, exponential distribution also no memory property. It has also no memory property. Right? If you can remember. In the note, it has given, so no memory property. Using the no memory property also we can solve this one. Probability of x greater than 15 given that x greater than 5. So in no memory property, it gives that x greater than x plus p given that x is greater than x. Then it could be written as x greater than p. Right? So here x is 10, sorry 5, t is 10. So by substituting that, we can write this one as probability of x greater than t. Now it's 10. So x greater than 10 is same as 1 minus f10 e to the power 10. Is it clear now? Any problem? Okay, let's move on to the next problem. Example 2. The number of automobiles that arrive at a certain intersection per minute has the Poisson distribution with mean of 5. So question 1 asks, what is the probability that more than 10 automobiles appear at the intersection in any given minute of time? And part 2, what is the probability that more than 2 minutes elapse before 10 cars arrives or 10 automobiles arrives? Try this one. Part A is a little bit easy, right? Part 1 is not about a continuous distribution. Why? It asks what is the probability that more than 10 automobiles appears. More than 10 automobiles means now it's not related to a time, waiting time. It's asking number of automobiles. right? So it's a discrete. You have to use here a discrete distribution. Try doing that. Only one has sent me answers. Yes, so one, your first part answer is correct. So what is the distribution there? So if we take the random variable there, number of automobiles that arrive at an intersection in a given minute follows a Poisson. Then first answer is correct. Second one is not. Okay, I'll explain. So part A, if we take the random variable x as the number of automobiles arrive at the intersection in a given minute, so number of automobiles, so it's a Poisson process, right? It's a Poisson process with lambda equals 5. Okay, lambda is equals 5. Per minute, it's 5. Right? So here lambda is equals 5. So we are asking what is the probability that more than 10 automobiles appear at the intersection in any given minute of time. More than 10, that is probability x greater than 10. Is 1 minus x less than or equals to 10. So this is same as writing 1 minus probability x equals 0 plus probability x equals 1 plus up to x equals 10. We can use directly the equation or we can use tables, Poisson tables, right? So it is 1 minus, using the table, this is equals to 9863. It is 0.0137. So here more than x means x, it exceeds 10. Therefore here it should be only x greater than 10. Yes, Tarushi, your part B answer is correct. Okay. Part B, what is the probability that more than 2 minutes elapse before 10 cars arrives? 2 minutes elapse before 10 cars arrives. කාර්ස් 10ක් එන්න කලින් ඔද ඔටෝමොබයිල්ස් 10ක් එන්න කලින් විනාඩි 2ක් ගිහිල්ලා තියෙන probability එකයි අහන්නේ. Right? So the probability they are asking is more than 2 minutes elapse before ten cars arrive. And it is same as saying less than 10 cars arrive in 2 minutes. Think of these two. Right? Cars 10ක් එන්න කලින් මිනිත්තු 2ක් ගිහිල්ලා තියෙන එක. ඒ කියන්නේ මිනිත්තු 2 ඇතුළත ඇවිල්ලා තියෙන්නේ 10ට අඩු කාර් සංඛ්‍යාව. So first sentence is same as saying less than 10 cars arrives in 2 minutes. පළවෙනි එකකින් කියන්නේ විනාඩි 2ක් ගිහිල්ලා කාර් 10ක් එන්න කලින් විනාඩි 2ක් ගිහිල්ලා. ඒ කියන්නේ විනාඩි 2 ඇතුළත ඇවිල්ලා තියෙන කාර් 10ට අඩු ප්‍රමාණයක්. ඒ ඉන්ටර්සෙක්ෂන් එකට. ඒ කියන්නේ less than 10 cars arrive in 2 minutes. ඒ විනාඩි 2 ඇතුළත ගත්තොත් කාර් ඇවිල්ලා තියෙන්නේ 10ට අඩු ගාණක්. So the same meaning. Right? So for part B, to solve the part B, there are two methods actually. We can use this one and use a gamma distribution, or else we can use this one and use a Poisson distribution. Right? So first we solve part B using the Poisson distribution. Right? That means this one. So let's take y, the random variable, as the number of cars arrive in 2 minutes. Right? So we know that number of cars arrive in a given minute, 1 minute, is a Poisson with 5. Now number of cars arrives in 2 minutes. So then the y, the random variable y, follows a Poisson with 2 lambda, that is 10. Okay. So less than 10 cars arrive in 2 minutes. That is probability y less than 10. So this is same as saying probability y less than or equals 9. So we can directly use table. So either this is equals to probability y equal 1, sorry 0, y equals 1 up to p y equals 9, or else we can directly use table. Then it is equals 0.4579. Okay, this is the way we solving this problem using a Poisson distribution. And we can use the gamma distribution as well. How? Let's take the random variable Z. That is waiting time. Waiting time for 10 automobiles to arrive. Or 10 cars, let's say cars for instance. Cars to arrive. 10th success. Right? Waiting time for 10 Poisson events to occur, where the rate of occurrence of Poisson event is 5 per minute. So waiting time for 10 cars to arrive, the 10th success. Waiting time until the 10th success. So now Z follows a gamma distribution with theta alpha, where theta is equals to now 1/5 because it gives us the lambda there. Right? Lambda is equals to 5. So now it's 1/5 lambda, it's theta, and 10th success. Right? So now we can write this. We want the probability Z is greater than 2, more than 2 minutes for the 10th success. Right? We want the probability. It will take more than 2 minutes to come 10 cars. So probability is Z greater than 2. Right? So it is same as saying 1 minus so greater than 2 means it's from 2 to infinity, right? F is a dz, but we can write it as 1 minus 0 to 2 f is a dz, right? So this is equals to, so now we can write f is z first. F is z is 1 over gamma of alpha theta to the power alpha and z to power alpha minus 1 and e to the power minus z over theta. Right? If we substitute the values for theta and alpha, then we can obtain gamma of 10 and 1 over 5 to power 10 into z9 and e to the power minus 5z. So this is equals to 5 to power 10 over gamma of 10 and z to the power 9 and e to the power minus 5z. Right, now we can write z greater than 2, that is equals to 1 minus 0 to 2, 5 to the power 10, and gamma of 10 can be written as factorial 9, and z9 e to the power minus 5z dz. Right, we can take 1 minus 5 to the power 10 and 9 factorial out, 0 to 2, z to the power 9 and e to the power minus 5z dz. So finding this one is little bit difficult, right? Because if we use integration by parts, right, you know, there are so many steps. You can try this at home, but you can use a calculator to obtain the value of this, right? You can use a calculator. The scientific calculator, it gives us the integral values. So we just want to input the function and then limits, then it will give us the correct answer. So the answer to the integral, this integral is 0.020143, right? So finally you will get the same answer, 0.4579. So the same answer, but using that Poisson is easy, right? Without using this gamma. So any questions up to now? Okay, any questions up to now? Okay, so let's wind up this session for today. So hope you get all the things. Please go through your notes again and prepare for the examination. And the normal distribution, this point onwards, Rakshan sir will take the lectures. Okay, so for the recordings, I will upload the recordings definitely within this week. Right, I have to do some editings as well, so I will upload them definitely. I will upload them, right? So any questions? Okay, so I wish you best of luck, right? Okay, thank you for participating.
Thank you, madam.
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 Thank you, madam. Thank you, madam.
Thank you, madam.
Thank you, madam.